clustering. So all of you know what clustering is, right? So we did it in the very first class, we looked at clustering, so all of you know what clustering is. Essentially the idea is to group together data points that are similar, right. So what you are essentially trying to do is find a partition. The simplest clustering problem is stated as follows: you want to find a partition of the data points such that the similarity between the points that belong to the same cluster is maximized, right, and the similarity between points that belong to different clusters is minimized, right. So that is essentially the thing. And so if I give you a set of n data points, right, and I ask you to partition it into k clusters, right, how many clusters or how many different clusterings are possible? So when I say a clustering, it is a set of k clusters, okay. So how many clusterings are possible if I give you n data points and k clusters and pose a condition that none of the clusters should be empty? Huge number, right, right. It's a nice question to ask in exams, right, but it's a huge number of clusters, right. So it's just impossible for you to exhaustively search through all the possible clusterings and then come up with the one that is the best, right. So inherently clustering is all clustering algorithms we look at are all some form of an approximation or the other, right, to the actual best solution. And in fact there are some statisticians who consider clustering an ill-posed problem, right, and do not deign to solve it, you know. I say, okay, that is an ill-posed problem, I will not solve it, right. So but the thing is, it is a real problem, people do need it. So all kinds of places where we look at clustering. So there are two main things that you do with clustering, right. So the first one is as a machine learning task, as a mining task in itself, right, I am interested in producing clusters, right. So I am interested in producing clusters, right. So this is some kind of a what we will call some kind of categorization. I want to take this this whole set of data given to me, and I want to categorize them into different groups, right. So in and of itself I am interested in doing clustering, right. Clustering is also very valuable as a pre-processing tool, right. So why would I want to do clustering as a pre-processing tool? So I can take a very large data set. If I have a cheap way of clustering it, right, I can cluster it, reduce it to a few data points, right. I can take say 10 million node data set, like 10 million whatever 10 million items, and then I can say I am going to cluster it into 10,000 clusters, right. Numbers are pretty large, it is going to take you a long time to do it, but at the end of it you will have only say 10,000 representatives of this 10 million data points. So I wanted to sample 10,000 data points from this 10 million, but I wanted to do it in such a way that they are as representative of the data as possible. So what I do is I use clustering, right, and so 10,000 is a large number of clusters, right. So each of those clusters is going to have a few thousand points, right, not very large, right. So then I can just go and pick out one representative for each one of these, as opposed to sampling directly from a 10 million node space, okay. So that gives me some kind of leeway, right. So pre-processing is another place where we want to use clustering, right. And any other thing that you can think of where clustering is useful? Exactly. Right. So for visualization, again, clustering is something that is very useful, right. Instead of just looking at a large table of data or something like that, if I look at it pictorially and I show you that okay, here are one set of data points that belong to one group, here is another set of data points and stuff like that, then it makes it a lot easier for you to understand the structure of the data that you are looking at, right. So clustering allows you to visualize the data and understand any kind of spatial structure or structure in the feature space, right. When I say spatial structure, does not mean that it is actually 2D space, right, it is I mean structure in the feature space. So is there any kind of structure in the feature space that you are able to understand that, right. So so it is a very valuable visualization tool and is also very valuable for you to understand something about your data, right. So in fact when I talk about categorization, right, so in and of itself it can be the problem that you are solving, or it could be something that you do as a pre-processing step before you go and actually solve the problem, right. So I might be interested in finding out how many classes are there in my data. So I do not know, say I have not been given class labels a priori, and I have not been given class labels a priori, but can I tease out class labels, right. Can I say that the data contains, seems to be coming from 3 different distributions, right, and then I am going to say each of those is a separate class condition distribution and I can assign a class label to all of those distributions, right. So it is like I am going to look at the data, try to understand it and then say okay, these are people who are likely to finish a course, right, these are people who listen to all the lectures but not write the exam. I do not know what it could be, so but you will have to look at the data to tell me that, right. So these kinds of things which you could do, this is what I am saying. Clustering is just not a one shot, okay, here give the data, here are the clusters and you are done with it. In fact quite often it is not even called clustering, it is called cluster analysis, because you do not stop with the clustering alone, you actually have to go and figure out what the clustering is telling you. Classification in some sense is much easier in some, so you are given something, you are basically return the labels and more often than not you are done, right. With clustering it is usually a step on the way to something else, okay, great. So there are many ways in which you can do clustering. So the most popular of this, okay, are called partitional approaches, right. So partitional clustering, and yeah, I will tell you what the others are, we will get to them once. So first thing is partitional clustering, then hierarchical and then density based. I mean they are not really disjoint classifications, right, but typically methods get indexed under these 3 and then there are many other smaller things, right. So somebody wants to get a paper written, they will say oh I propose something that is neither partitional nor hierarchical, and then they will propose a new algorithm and things like that. So that is just to sell their paper, not necessarily separate classification, right, but these are kind of the 3 main classifications, right, and so we look at each in turn, right. Partitional clustering things, k-means, everyone knows what k-means is, right. So why do we call them partitional clustering? Clustering is partitioning the data, right. So why am I calling these as partitional clustering? So I am essentially, these are methods which search through the partitions directly, right, the final partitions that I want, right, they search through those partitions directly. So that is why they are called partitional clustering methods, okay. So in the as opposed to hierarchical clustering methods, right, which do not search through the space of partitions on the entire data set, right, they first try to do it into 2 groups, right, they do not search through all the partitions. Suppose I am interested in k things, right, they do not do all the k, they do not do the k clusters, right, they can start off with 2 clusters and then split the 2 clusters into 4 and so on and so forth, okay, it can go down into that, they do not search directly in the space of k partitions, right, while k-means exactly does that, right. Just when what do you do in k-means, I am sorry, so what do you do in k-means, you start off with k guesses for the centers of the clusters, right. So there are few things that we need to know. So the first concept here is the centroid. So what is the centroid? Well, it's the center of a cluster, right. So essentially you take the average along each coordinate, right. Suppose I have 10 points that belong to the cluster and it is in a 5-dimensional space. For each dimension I take all the 10 coordinates, take the average, right. So finally I will end up with a single data point. So that is the centroid, right. Suppose I have some set of data points like this, right. So the centroid could be somewhere there. Not that I am exactly computing the centroid, but it will be somewhere there, right.
Rather than random guesses, what do we start off from the approximate solution, the two approximate?
Sure. So what is how do you find the approximate solution?
We start off from any one point and choose the farthest point from that. And
yeah. So there are many ways of cleverly initializing this, right. So I am just talking about the plain vanilla k-means, right. So there are many ways in which you can look at a clever starting point, right. So there are other things which people do. What they do is they start off with a 10% sample of the data, right. They start off with a 10% sample of the data and then they repeatedly run clustering on that and figure out which are the good centroids for that 10% of the data, and then they use that as the initialization and do the clustering on the whole data, right. So the idea there being the number of repetitions you would need is very small, because you are only doing many repetitions on 10% of the data but not on the whole data. So that is one way of doing it. So other way of doing it is to do this kind of an initialization where you try to move to the farthest corners, but then that has its own problems, right. So essentially it will make it more sensitive to outliers, right, because you are trying to put your centroid, the beginning centroids at the edges of your space, right. So it will make it more sensitive to outliers. So those are issues.
One way is you could like run that once and you could then create all those clusters and then choose the centroids of those clusters.
Yeah.
Which essentially k-means.
Which essentially k-means.
Yeah.
What is?
First you take some centroid, then you have.
Yeah, that's k-means. Yeah, that's. No, I don't think he meant that. I think he meant something else. We'll come to that, right? So I mean, there are. Again, many heuristics. So I think the current k-means variation champ is I think called k-means plus or something, right? So that gives you a very good initialization, and then you run your clustering from there and works well, right. But k-means is an approximate thing. So when you look at EM, right, so you will actually see a more well-founded derivation for k-means. So right now I am just going to introduce it to you as a heuristic, right, but later on when you look at EM, right, the canonical EM problem that you will solve, right, first canonical EM problem that you look at will be k-means. Well, a variant of k-means. It usually we call Gaussian mixture models, but it is essentially like k-means. Okay. So what you do with k-means is that you first pick centroids for all your clusters, right, randomly. Right. Suppose I have k clusters, then I will just choose So I will choose k centroids at random, right. It could even be like that. I choose k centroids at random, and then I will have my data points. So what I do is I assign each data point to the centroid that is closest to it, right. I assign each data point to the centroid that is closest to it. Okay. Now I forget the old centroids. Now I have k groups of data points, right, and for each of those groups I try to find the new centroid. Right. This is the actual centroid. The first ones I started out of centroids were really not centroids, but we still call them centroids anyway. So just to keep the terminology uniform. Right. Now I recompute the centroids. Then I go back and assign each data point to the centroid that is closest to it.
Closest means physical distance.
Yeah, whatever distance measure you are using. Right, so you are in some RP space, right. You remember our data points come from some p-dimensional space. So in that space, whatever is nearest, you could use Euclidean, you could use whatever distance measure you want. You choose the appropriate distance measure. right. So k-means or any of these distance based computations that you do, right, works best. Okay, any of the distance based computation you do works best if everything is real valued, right, not even integral, right. So everything is real valued, it works best. If you are going to have categorical attributes, you will have to think of a different distance measure that you will have to define, and I do not know if yeah, maybe I can talk about one or two things that people use for categorical things, but the most popular by far is using some kind of Jaccard similarity, right. So I have lots of values that the thing can take, and then I say, okay, how many of those it actually is similar on, right. Right, so how many dimensions am I actually agreeing with the other one on? So if I have the same value in that categorical dimension, then I will say 1. If I don't, then I will say 0, and then I will try to find how many I agree on, right, and that could be one measure. But then defining a centroid there is a little tricky, right. It's a categorical variable. My centroid might come with a value of, you know, red 0.5, or I mean like 0.5 times red plus 0.5 times green, right. So what would that mean? No, don't add up the colors, please. I mean, huh? What's that? Brown or something. I don't know what red and green would end up in, but don't know, that doesn't make sense, right. So we have to be very wary about using k-means when you have categorical attributes. Yeah.
When having categorical outputs, could you look at it as a probability vector or something? And you'll be increasing the dimension of your input space, I guess, but
So what do you mean by probability vector? Like a 1 of n kind of encoding, is it?
yeah.
One hot encoding, right?
Start off with one hot and
Yeah, you could do that, but then really what would be the mean, the centroid value for that 1 hot encoding?
it's like adding up to, I mean, if I have 1 point with this probability and this point with this probability, it's like adding that because you weight and add.
Yeah. Yeah, that's a interpretation issue. So you could still try k-means. I mean, you don't really have to interpret what the centroid means unless you are returning the centroid as a representative point, right. If you are returning the centroid as a representative point, then you get into problems. If you are just going to do clustering on it, you can go ahead and do clustering on it. You don't have to really interpret the value of the centroid, right. So there are ways of handling this when you have categorical attributes, right. So k-means is the simplest way. Then there is something called k-medoids, right, which kind of gets around this whole issue of having to generate an artificial centroid, right. So instead of a centroid, it essentially uses the equivalent of a median, right. So the mean need not actually be a data point, but the median is always a data point, right. So likewise, a medoid is always a data point. So it gets around this interpretation issue. So it computes the centroid and takes the data point closest to the centroid as the representative. So that's the medoid, right. And then you also have other kinds of things which is called partitioning around medoids, right. So when you do partitioning around medoids, you work with the data points as the representative of the clusters, right, and you don't ever generate an artificial point. You always choose another data point as a center. I'll describe that more, right. So in such cases, you don't have to worry about this you know, meaningless attribute values being generated, but you still need a distance measure. So you'll have to come up with some kind of a distance measure, which if with categorical attributes. So if you use 1 out of n or 1 hot encoding or anything else, you can still use some kind of a Jaccard similarity, right. So then do that. Okay. Right. So going back, let's finish up the simple k-means algorithm, right. So what you do with k-means is, so once you have done the assignment to the centroids, you forget the centroids, estimate new centroids, and keep repeating this until you no longer make any changes, right. So are you done? Huh? No labels business here. There are no labels. It's an unsupervised learning problem, right. So if you have labels and other things, I mean, depending on what your application is, you might want to look at labels, right. As far as k-means is concerned, the question is the following. I start off with an initial guess for the centroids, right. I assign data points to the closest centroid, then recompute the centroids, then reassign the data points to the closest centroids. I keep doing this until the centroids no longer change. The question is, am I done?
Is that the centroid would always like a cyclic dependence. Consider an equilateral triangle.
Consider a
Points. Suppose we use Euclidean distance.
yeah.
We have an equilateral triangle as our 3 data points,
Okay.
and then
Where are my, how many clusters you want me to put them into?
3.
3 clusters. I am done.
But it depends on initial choice and.
You are getting close. So the probability of me cycling is really really small. Yeah.
You could end up with, I mean, 2 of the centroids could be at the same point. You may end up with only k minus 1 clusters.
Yeah, but there are other things which I can show which is slightly more dramatic, right? Okay, these are my 2 sets of data points. Obviously, they are in 2 clusters, aren't they? These are the 2 initial centroids I start off with. Okay, so what are the 2 clusters I will get? Okay, and I compute the centroids for those. Where will I end up in? And I reassign the data points to the centroids. I will end up with the same thing, right? So because of my bad initial choice for centroids, I do end up at a point where the centroids don't change anymore, but it's a really bad clustering.
Isn't this why you have random points?
Yeah, I randomly chose those 2 points. Like I randomly chose things. I mean,
Yeah, multiple times.
huh?
Okay, that's a good
Exactly. So my question to you was, if your clustering doesn't change, are you done? The answer is no. Okay. In this case, surprisingly, one of the few cases where the answer is not, it depends. The answer is no. Okay. Because if you just do it once, right, you are not done. That's the thing with k-means. You will have to repeat it multiple times, right? And please, every time use a different random seed for choosing your initial starting points, right? If you choose the same random seed, then you will get the same thing, right?
So in this k means, how do you select the value of k?
Yeah, we'll come to that, right? And right, so but people understand why you have to do this multiple times, right? Because you will get stuck in some kind of local optima, right? And you have to start over again with a different random set of k centroids, right? And then keep doing this. Yeah.
So, how do we assess how do we check whether the clustering is good or not at the end of the procedure?
Good point. So there are different measures. I never told you about cluster evaluation measures so far, right? So there are different ways in which you can evaluate clusters. So one of the more popular one is some kind of a dispersion measure, right? So I can look at diameter. So the way the diameter is defined, there are 2 definitions unfortunately for diameter in the literature. So the first one is the average pairwise distance between the data points that belong to each cluster, right? So if you took that, right, so I will take the pairs of data points, right? I will measure the distance between the pairs. So but then I will also have to consider pairs like that, right? So I will look at the distance between every possible pair of points that belong to the same cluster, right? And I will take the average. Okay, that will be the diameter of this cluster, and the average of the diameters of all the clusters will be the quality of the overall clustering. Okay, that is some kind of a dispersion measure, right? So how much spread out my data point is. right. Alternatively, if you have if you are computing centroids, right, you can also compute the average distance of the data points to the centroid, right, and take the average across all the clusters and use that as your quality measure, right. So either one, I mean, is referred to as diameter in the literature. So some call the more popular one is the average pairwise distance. Okay, is it fine? Right. I take it back. I take it back. So the average distance to the centroid is called the radius of the cluster. Okay, the average distance to the centroid is called the radius of the cluster, right. So the diameter, the second definition of diameter is the max of the pairwise distances, right. So you could either do the average of the pairwise distances, right, or the max of the pairwise distances, both could be called the diameter, but the radius is essentially the average of the distances to the centroid. Okay, so this is one measure, right. So there is another measure which you could think of, which is essentially it's called purity. Which, did you guys look at purity already? We never gave it to you in the first in any of the assignments so far, right. So purity essentially tells you for each cluster that you have, what fraction of the data points belong to the same, belong to one class. What is the largest fraction of data points that belong to one class? Okay. So purity can be used only when you have data sets that have class labels associated with them, right. So suppose I have 10 data points that go into one cluster, 6 of them are in class 1, 2 are in class 2, 2 are in class 3. So the purity of that cluster is 0.6, right, because 6 out of 10 are in class 1, 2 out of 10 are in class 2. So 6 out of 10 is the largest thing, so 0.6 is the purity of the cluster. So like this.
What about the hierarchical one that you thought? Multiple classes are meant to be.
So whatever, right, so whichever level of hierarchy you are evaluating it at, you will have a set of clusters, right, you just evaluate the purity. If purity is a measure that you choose, right, so that does not matter. So purity makes sense, right. So something related to purity, again if you are using label data sets, you can use something like entropy, right. So what would be the entropy? I mean, it is essentially the class distribution, right. You look at the class distribution in the cluster, right. So if if P1 fraction is class 1, P2 fraction is class 2, so you can just do minus P1 log P1 minus P2 log P2, right. So that is essentially the entropy. So this if the classes are more or less evenly distributed, then the entropy gives you a better measure than purity, right. So if I say the purity is 0.5, okay, it is not clear to me whether the other 0.5 belongs to the same class or whether they belong to many different classes, right. So that's the thing, right. So these are the measures that you could use, and then I mean like a zillion. This is why statisticians say that clustering is a ill-posed problem, because there are many different evaluation measures for clustering. So I am just trying to list some of the more popular ones, okay. And there is another one called the Rand index, which is typically used when you have a reference clustering, right. When I have a reference clustering and I am trying to achieve that reference clustering, right. So what do I do? What is the Rand index? Is for good point, but I do not have class labels. So I have a reference clustering, but I do not really have class labels. So when the new data comes into me, I do not have class labels, right. It is not like I am assigning data points to classes. So the new set of data, new data point will not come, I will have new set of data, and I should run this algorithm on that set of data and produce a clustering, right.
No, but if you do a classification on the original data,
Yeah.
and you just use this new data as a test case.
Sorry.
the new data that you get,
Ah.
use it as a test data. So that then you get the
possible. So, but the point here is I am not really looking to reproduce exactly that clusters, right. What I want to do is the following: I give you a data point, I run a clustering algorithm on it, I give you a set of clusters, right. So, I would like the clusters on the training data to look like this. So, now you give me a new set of data points, then I will run a clustering algorithm on it, I will get a set of clusters, I am a little bit more comfortable with that set of clusters because on the whole data point I managed to reproduce the reference clusters. So, the new set of data points I get might not actually directly map to the old data points itself, right. So, this is a slightly different problem, right. So, I am just evaluating my clustering algorithm, not a single clustering that was produced, right. So, one way to think about it is to think of it as the RAND index, right. Of course, there are cases where you would like to solve classification problems as clustering problems. One instance would be that you have nicely separated classes, but many of them, right. So, that is another case, but I am not talking about this. RAND index is typically used to evaluate how good the clustering algorithm is, right. So, what you do here is you take every pair of data points in your data set, every pair I and j, right. So, if xi and xj belong to the same cluster in the reference clustering and they belong to the same cluster in the clustering that you produce, give yourself a score of 1. Okay. If xi and xj are in different clusters in the reference clustering and they are in different clusters in the cluster that you produce, give yourself a score of 1, right. How many such pairs are there? N choose 2 pairs are there, right, n choose 2 pairs are there. So, divide this sum by n choose 2, right. So, what it tells you is of what fraction of pairs of data points have you clustered correctly, right. So, what is the nice thing about RAND index is, suppose you are little bit more selective in your clustering than the original the reference clustering that was given to you, right. You end up splitting some data points, splitting some clusters into 2, right, while original clustering gave you a larger clusters, right. So, the original clustering said, hey, this is my reference cluster, right, and you end up producing this and this as 2 clusters, right. So, RAND index does not suffer greatly, right. It is only the cross cluster pairs that get penalized, but within cluster pairs are all fine, right. So, it gives you a little bit of leeway in terms of being stricter than the other than the reference clustering, okay. So, these are different measures and you can use whatever you want, right, of course not RAND index, right. You can use diameter or radius in this case, right. If you have a label data points, you can use purity or entropy, or I mean there is a whole measure of these, okay. So, we can go and list about 100 of these measures that people have used in the literature, just pick your favorite one.
If we have a reference cluster, why do we need pairs? Why can't we query on a single point?
Good point. So, how do I know which cluster is what, right?
If we have a cluster, we can just query a point on.
No, see, I have to figure out, then I have to do an alignment on the clusters, right? See, I have some K1 clusters I have produced, that is my reference cluster. My reference cluster has K1 clusters and I have produced K clusters. So, how do I align this K to the K1? Right. So, RAND index gets rid of the alignment problem. Okay. Oh, okay, go on.
also look at if some clusters are repeating across multiple ones of the
Some clusters, huh?
a few points are always in the same cluster when you are running it multiple times. We're running k means
Yeah.
a few times.
Yeah.
So if they are always in the same cluster,
Yeah.
we can always fix that centered.
Yeah, there are many ways in which you can do these optimizations. Right? There are literally hundreds of papers out there which try to do this kinds of optimizations. So the question is, yeah, what is the overhead in implementing these optimizations, and whether in your particular application, whether that overhead is justified. because you are getting a significant improvement over the usual way of doing things, right. So what people do as standard implementations are things which kind of give you good results across a variety of domains. If there is something very specific for your domain, then you are welcome to try do those optimizations, right, and that is what makes this an engineering discipline as opposed to theory, right. So yeah, so there are many things that you can do, right. So going back, great. So now I did this, I do this again, I keep doing this multiple times, and what do I do with all the clusterings I produce? Huh? Take the best, yeah, take the best, yeah, that's right. So there is no nothing. So you just keep doing the clustering, and whatever evaluation measure you have, so you take the best according to that evaluation measure. Okay, so you throw away the rest. Right. So you have to repeat it a few times, and then take the best. Great. Okay, let me reiterate again. Okay, you have to repeat k-means multiple times. Please don't come to us after doing k-means once and say that, oh, that doesn't seem to work. Okay, so I will guarantee you that one time it won't work. I mean, we don't know, but just making that emphatic. Okay. So let's go back to the question: how do you fix k? How do you fix k? Great, that's one answer. What is your answer?
Domain knowledge.
Domain knowledge, yeah, that's exactly, I mean, so depending on user requirement, domain knowledge, right. So domain knowledge is one way of fixing k, right. Is there another more systematic way of fixing k? Huh? Try all k's, but then how do I know which k is good? So I'll tell you one thing, say suppose I am using diameter as my measure, right. The larger the k, the better it is.
You can penalize the larger, you can penalize
Complexity.
Exactly. So the right way of doing it would be to say that I am going to have some kind of a complexity performance trade-off, right, but it is incredibly hard to implement in k-means, right, incredibly hard to implement in k-means. So, but you can do that, I mean, people have come up with that. So especially if you are going to take a Bayesian approach to clustering, right, if you take a Bayesian approach to clustering, how will you implement the penalty for the size, for the number of k? The prior, what will you do with the prior? Who said prior? What will you do with the prior? How will you make it penalize larger k?
1 by k as prior.
Exactly. So reduce the prior probability for large k, right? But then you do the searching. The main problem with this is most of this optimization thing is for finding clusters work well if I fix k, but if k becomes a parameter in the optimization, it becomes incredibly hard. That is why I said it is hard to implement, right. If k becomes a parameter in the optimization, it becomes incredibly hard to solve the problem, right. So for fixing a k, right, you can think of k means as a approximation to solve the fixed k assignment problem, right. Even if for a fixed k, if I have to do something like k means to solve it, if I am going to make k a parameter and try to solve the larger optimization problem, right, it becomes a little tricky. So as opposed to that, so what people do is a practical thing is draw a curve between k and, let us say, draw a curve between k and diameter, right. So what would you expect to see as k becomes larger? Decrease. You will see something like that. It will keep going down, yeah. It will keep going down to 0, I mean, depending on how many data points you have, right. So if you, so at k equal n, it will become 0. No, you don't have to do all of that. I already told you what the right value of k is here. I have shown an example, so trick here. What is the thing happening? So as my k initially decreases, you can see a rapid decrease in the diameter, right? After some point what happens, this thing slows down, right? So if you think about it, there is a significant change of slope somewhere around here, right? So that essentially quantifies your good K complexity versus performance trade-off. So wherever there is this change of slope, right, you pick that point and say that this is the right K to use.
Wouldn't the computationally expensive case like a very large value you have to try?
Usually it's you do this when you are trying to identify a small number of K, right? If your K is very large, right, then you are probably using clustering for some kind of pre-processing rather than as the final means, okay. So if you said, you remember, right, I told you that there are different ways in which you use clustering. So if your clustering is the K is very large, right, you are probably using it for some kind of pre-processing, right, in which case the exact choice of K does not matter that much, right. When you are trying to use it as either as a visualization tool, even visualization the choice of K does not matter that much, but if you are using it as a actual end in itself, right, you want to do clustering, you want to do categorization, in those cases typically you have K is smaller, right, but you can run K up to a few hundred, that is fine, right, and then you can find the right value of K like this, right. But if determining the right value of K is of some crucial importance to you and K is very large, then I would not recommend partitional methods at all, right. So I would recommend other approaches for doing the clustering, okay. So this is called the bend. Now what did he say? So there is a name for this, a very descriptive name, it is called the knee method, knee. So it bends, right. Right, so it's called the knee method for identifying K. Okay. So in fact you can use this for in other cases also where you want to do this kind of complexity versus performance trade-off, and the optimization problem becomes very hard if you throw in the K into the complexity parameter also. If you throw into the optimization problem becomes very hard. So you can use this kind of a empirical method for determining the actual value. Okay, good. Can we move on? Right. So what about K medoids? It's like K means. So you find the centroid, right, and the representative you use is the guy who is closest to the centroid. Right. So at every point of time you have a representative which is an actual data point, right, and then when you do the assignment you assign it to the medoid that is closest to you. Okay, not a very interesting thing, but the advantage of this is when you move from average to median, mean to median, what is the advantage in statistics? It does not get affected by outliers. Same thing here. So when you move from centroids to medoids, okay, it becomes a little bit more robust to outliers, right. Suppose all of this is the data points, right, and I try to cluster it, right, so I will end up getting a centroid somewhere there, right, then but the medoid might be this, it's slightly better, not that much, but better than having a centroid that is out there. Okay. So one important thing I forgot in application of clustering, something called outlier mining. So what is outlier mining? Well, find outliers, right, I mean there's nothing, no big deal about it. So why do you want to find outliers? Delete them is one of that. Anything else? Sorry? Fraud detection, right. So I want to do any kind of anomaly detection. So outliers would be anomalous data points. So who said fraud detection? Sorry, okay, yeah. So the outliers would be some kind of anomalous data points, and therefore you would want to find them. I am not interested in deleting them from the data set, right. I am probably interested in deleting them from the real world, right. So that I want to catch these things and put them, right, so safeguard against them and things like that, right.
So will it be useful for undersampling
Yeah, that's one of the initial things I told you, right. So instead of randomly sampling over the entire state space, right, generating 10,000 samples from a million sample database, do clustering, do clustering with k equal 10,000, right, and then sample one from each cluster. Okay, that gives you a more representative sampling. I mentioned that as one of the uses in the very beginning. Yeah. Okay, great. So we have done k means, we did k medoids, right. Let us do PAM. Okay. So PAM is called partitioning around medoids, right. In fact, it is incredibly expensive algorithm, right. Nobody uses PAM anymore. Right? When it was proposed, it was a very big thing, and then but then people came up with the faster ways of doing PAM, and all of this work on very small data sets. Okay, I mean on really large, if you want to do 10 million data points and things like that, PAM is nowhere near competitive. Any of these medoid based methods are not at all competitive on very large data sets. Okay, and but anyway, I will just talk about it because it's a very interesting algorithm, right. So in partitioning around medoids, so what you do is, so I have some data points. I start by assuming some, let us say I am doing 2 clusters here, right. I am start by assuming some 2 data points as my initial medoids, right. So let us say that I start by assuming this as one medoid, right, and unfortunately I assume that this is the other medoid, right. So now I look at the quality of this clustering. Let us say I use radius as a measure for quality, right. So I will assign all the data points that are close to right. So I end up this as one cluster, right, that as other cluster, and then I look at the average distance of the data points to the medoid, and I keep that as my quality of this clustering, right. Now what I will do is, for every medoid, right, I will consider swapping it with a non-medoid. For every medoid I will consider swapping it with a non-medoid, right. So I will say, okay, no, I will make this a normal data point, right, let me make that a medoid. Okay, now if I make that a medoid, what is the change in the quality of clustering, right. So likewise, so for this medoid I will consider each non-medoid in turn, okay, and consider swapping with it, and then whichever gives me the best improvement in clustering I will keep that as my new medoid, and then I will go look at the other medoid, right. Now I will consider swapping this with each one of the data points in turn, right, and then maybe I will swap it here. Sorry?
We would swap it with the data point in its own cluster?
No, anywhere. So this is how it works. It's very expensive, I told you, right. So for every time you do the swapping, you do order n thing, right. Is it only order n thing? No, why? I just still have to check the distances. That is, so checking the distances is another order n computation, right. So I essentially end up doing n squared computation for every swap that I have to make. Okay, then people made all kinds of interesting observations, and they came up with ways of cutting down on the number of computations that you do per iteration, right. So when I make a swap, right, I do not have to go through each and every pair, right. So only those that change cluster membership, right. Only those data points that change cluster membership I will have to really look at it. So data points that belong to the current cluster, right, the medoid of which I changed, obviously I will have to do recomputation for that, right, and among all the data points that do not belong to that cluster, only those that change cluster memberships I will have to evaluate this, right, but then I will have to evaluate the cluster memberships anyway, right. So I do not have to do new things, but I will still have to evaluate cluster memberships. So but then you can again organize that a little more efficiently and so on and so forth. So depending on how you organize this computation, people came up with a variety of different things. At least PAM I can remember, it is partitioning around medoids, right. So I'm people are interested, I can give you pointers to read up more on PAM and Clarence and things like that, but like I said, it's not very that widely used in the community, so we'll skip those things. So what are the problems with k-means that PAM addresses?
The randomness of the initial randomness.
The initial randomness really doesn't matter anymore, right? Because I am anyway considering everything, right? I am anyway considering every possible pair that's gone. Then, well, it's medoids, therefore it is no longer, it's not that affected by outliers, right? What about the choice of k? I still have to choose k. That's still there. That has not gone away, right? And what about this issue that k-means works only if you have real valued attributes? Works well if you have real valued attributes. Have you gotten rid of that? I still need a distance measure, right? So if I am going to have categorical attributes, I better have a distance measure that takes care of categorical attributes. So still that those problems still remain with PAM. Okay, great.